Hi, everyone. Welcome to Module 4, Lesson 3. Today we're going to talk about polarity and intermolecular forces. So in order to determine polarity, we have to go back to our electronegativity, which we know is the attraction an atom has for a shared pair of electrons. We talked about that in atomic structure. If the bond is between the same element, they share electrons equally. If one nucleus has a higher electronegativity, it's going to pull the electrons closer because it wants those electrons. And so there are two types of polarity. There are nonpolar bonds and there are polar bonds. So nonpolar covalent bonds are covalent bonds that share electrons equally. Polar covalent bonds are covalent bonds that do not share electrons equally. And there's a general chart here that we can talk about. If the difference in electronegativity values is about 2 or above, it's ionic. You should also know what's ionic just because that's a metal and a nonmetal. If it's polar, it's about in between 0.5 and 2. Nonpolar is less than 0.5. What you want to use, and again, all electronegativity tables are not made the same. So I've posted one here. So I want you to use the one that's posted in the modules. This is what it looks like, and it gives you all of the electronegativity values for the different elements. And that's what we're going to use. So a couple of bonds that you must know about the polarity-wise. There's going to be the CH bond. That's an important one. The CO bond and the OH bond. So we're going to go onto our table here of electronegativity values, and the value for C is going to be 2.5. Okay, so let's go back here. Carbon, no, of course it went away. So carbon is 2.5. Let's see what oxygen is. 3.5, and hydrogen is going to be 2.1. And those are the three we need for our examples here. So, sorry, I'm flipping back and forth. So for CH, carbon was 2.5 minus 2.1, which gives me 0.4. The CH bond is non-polar. Okay, and that's how we do this to determine if it's going to be polar or non-polar. You just take the bigger one and subtract it from the smaller one. It doesn't matter if it's CH or HC. We just take the bigger number and subtract it from the smaller number. Excuse me. So CH is a bond that you're going to see a lot. Please note that it is non-polar. For carbon and oxygen, okay, so oxygen was 3.5 minus the 2.5 from carbon, and that's 1.0. That's going to be a polar bond. So the carbon-oxygen bond is polar. And then for the OH bond, that's 3.5 minus 2.1, which gives me 1.4, and that is going to be polar as well. So that's how we do this for our bonds. But these three are ones you're going to see a lot. So it's going to be really helpful if you just know CH is nonpolar, CO is polar, OH is polar. Okay. And that's really it. There's practice on this, but it's not too difficult. We're going to take all of the concepts that we do today and incorporate them into, and the stuff from the lesson 2, all of that is building up to the 4th lesson, which is the super important lesson that's coming up after this. So let me just clear this. Did that in the last one. And so the other thing we're going to talk about is intermolecular forces. And like I said, we're going to pull this stuff next lesson as well. So intermolecular forces, so it says molecules can be attracted to each other by a variety of different forces. Intermolecular forces are weaker than either ionic or covalent bonds, but they are important. And intermolecular forces are the forces of attraction between molecules. So for example, here I have iodine molecules. What attraction do these molecules, these individual molecules, have to each other? Well, here we've got our first example is London dispersion forces. London dispersion forces are the weakest form of molecular attraction that are caused by the random motion of electrons. They occur between nonpolar molecules. So nonpolar molecules only have London dispersion forces, okay? But everything has London dispersion forces because everything has electrons. So what happens? At any one given time, any moment in time, one of these iodines, so there's just electrons that are floating around these iodines. At any one given time, I can have more electrons on one of those iodines than the other. When that happens, you can see that you've got more electrons around this iodine here, and it's got this little symbol here. That means that it's partially negative. So that side is partially negative. The other side is partially positive. And then once that happens, all of the other ones, basically all the other molecules around it align in that orientation so that the partially negative one iodine of one is attracted to a partially positive iodine of another. All right, and so you see those two things are going to be attracted to each other. So it's going to be between molecules. So everything has London dispersion forces. If you're a nonpolar molecule, you only have London dispersion forces. And if you're comparing things that just have London dispersion forces, how do you know which one's going to have stronger London dispersion forces? The more electrons, the stronger the London dispersion forces. Okay, and so that's our weakest. So let's go to the next one. Dipole-dipole. Dipole-dipole occur when we have polar molecules. Again, so we talked about polar bonds. We're going to talk about molecular polarity in the next one. So again, we're taking all of this stuff, building up until the last lesson. So dipole-dipole interactions occur when polar molecules are attracted to one another. A dipole moment is a partial charge at the end of a bond that is equal but opposite. So we had a dipole moment in London dispersion forces, but that was random. In dipole-dipole interactions, you have a set dipole moment all the time because something is always going to be partially positive, something's always going to be partially negative. And in this case, we've got hydrochloric acid. Hydrochloric acid, the chlorine is much more electronegative. And so that's the partially negative, and it will always be like that. So if I have Lewis dot structure of hydrochloric acid, we know that this is going to be a polar bond. And so the chlorine's more electronegative. And so to show where the pull is, so the electronegativity, basically the electrons go towards the more electronegative thing, and then you'll see like there's a line on the part where it's partially positive. So this is showing me my dipole moment. It's getting pulled towards the chlorine, and the hydrogen part's the positive part. And so the attraction of a dipole-dipole interaction is the attraction between the partially negative chlorine in one hydrochloric acid molecule to the partially positive hydrogen in another molecule. And that's your dipole-dipole. And then finally, hydrogen bonds. Hydrogen bonds are going to be our strongest intermolecular force. So hydrogen bonds to a very electronegative atom. It's also weakly bonded to an unshared electron pair of another electronegative atom. So basically what this means, if hydrogen is having fun, then there are going to be hydrogen bonds. So if a partially positive hydrogen is attracted to a partially negative fluorine, oxygen, or nitrogen in another molecule, you will have hydrogen bonding. Okay, so water is a good example. You've got partially positive hydrogen is attracted to the partially negative oxygen in another molecule, okay? And the hydrogen has to be partially positive, okay? And it doesn't matter if it's bonded directly to that, okay? It just needs to be attracted to in another molecule, okay? Now, what's that something I'm doing? Hi. What are we going to really be doing this? So when comparing two compounds in a question, first determine the type of chemical bond involved for each substance. If the bond is covalent, we're going to look at our intermolecular forces. Second, identify the property to be explained and discuss the chemical bond, and if relevant, the intermolecular forces for each substance relating to the strength required for the event to occur. So this is the important part, this last part that's bolded. When physical changes occur in molecules, bonds are not broken, only the intermolecular forces are overcome. So for example, when liquid water goes to a gas, it takes a lot of energy to boil water, right? And that's because water has hydrogen bonds, dipole-dipole interactions, and London dispersion forces. So they're like additive. So if you have hydrogen bonds, you have all three. If you have dipole-dipole, you have dipole-dipole and London dispersion forces. So getting back to this example, when you have liquid water going into the gas, it takes a very long time to heat up water. One of those reasons why is because their intermolecular forces are so strong. To go from a liquid to a gas, those molecules need to separate. Okay, so you need to put in enough energy to break the intermolecular forces. Okay, we're not breaking any bonds, but we're just breaking intermolecular forces. So the stronger those intermolecular forces, the more difficult it is going to be to break those bonds, and therefore take longer or require more energy to overcome. Let's look at some other examples. So, carbon monoxide. It's a C and an O bonded together, and that's going to be polar. Okay, that's a polar bond, right? So, since it's a polar bond, it's going to have dipole-dipole interactions, and London dispersion forces. So you can see that it builds up, okay? So let's say I had CH4 versus C2H6, okay? And let's just draw the Lewis dot structures just for practice. So we know that when things are bonded to themselves, their difference is 0. And when we went through this, the CH bond is nonpolar. So these are both nonpolar. Which one is stronger? Which one has the stronger London dispersion forces? Okay. And what we want to do is we want to look at our electrons. So you can look at total number of electrons, but in general, the mass and the number of electrons are related. So the more mass, the more electrons you have. So you don't necessarily always have to look at the number of electrons. That's what you're technically supposed to do, because sometimes that does not work, but 99% of the time it's going to work like that. And so therefore, the C2H6 is going to have the stronger London dispersion forces. Why? Because it has more electrons. Okay. Now, that's it for this. Okay, we're going to talk much more about intermolecular forces, polarity, and our Lewis dot structures in the next lesson when we bring it all together. So in Module 4, Lesson 4, we're going to bring all of this information together, and we're going to talk about molecule shapes. So If you have any questions, please ask them. I know some things might be a little iffy because we have more to talk about them, but if you have any questions, please feel free to ask them in the chat or ask them in class. All right, I'll see you later.